Let's first take a look at the polar moment of inertia for a solid circular shaft. The polar moment of inertia of a shaft is defined as the integral, over the domain of the cross-sectional area of the shaft, of the elemental area dA multiplied by its radial position from the axis of the shaft squared. For this derivation, we will designate the radius of the shaft as r and the radial position of the shaft as ρ. If we consider a small change in radial position, d ρ, and sweep this small change in radial position around the axis of the shaft, we define an element of area shown here in purple. For a small change in radial position, we can define the area of this element as the perimeter multiplied by the radial position change, or dA is equal to 2 pi rho d rho. Thus, the entire area of the shaft will be covered by increments of d rho in the radial direction. Transferring this result to our integral, we can define a definite integral over the range of radial positions within the shaft. For this solid shaft, the lower limit thus becomes 0 and the outer limit becomes the radius of the shaft, r. Substituting our result for the element area dA, we can expand this integral to the following. Removing constants from the integral and collecting terms, we can then simplify. Integrating rho cubed, we obtain 1/4 rho to the power of 4, resulting in the following. After substituting in our limits of r and 0, we obtain our final expression for the polar moment of inertia of a solid circular shaft. Next, let's consider a hollow circular shaft with inner radius r1 and outer radius r2 as shown here. The definition of polar moment of inertia does not change. Furthermore, a small change in radial position d rho produces the same area element as before with a solid circular shaft. The only difference in transferring this result to our integral is that the limits of integration are changed. The integral is performed from the inner radius r1 to the outer radius r2. Substitution of our element area into the integral, simplification, and subsequent integration of the result remain the same as before. However, due to the different limits on the definite integral, the final expression becomes a function of the inner and outer radius as shown here.